So good afternoon. My name is Brecht Devolder. I'm working for DEME, a marine contractor. I'm working for the engineering department in the activity line dredging, and I'm working as an expert engineer, computational fluid dynamics. And today's talk goes about how we enhance our sustainable marine solutions and operations by running STAR-CCM plus CFD simulations on the VSC supercomputer. So what's on the agenda? First, I will start with an introduction about what is DEME and what do we do. Then I will talk a bit about why is a marine contractor doing complex flow simulations? So how do we do and why do we do CFD simulations within the engineering department? The main focus of this presentation is about how we accelerate our CFD simulations using the Flemish supercomputer. And then I will end with some conclusions and take-home messages. So first, let me introduce DEME with a movie about 90 seconds with what we're all doing. So yeah, please enjoy the movie. So that was a short introduction about our company. So you have seen quite some movies of vessels and water. So we are a marine contractor and everything is linked to water. And we try to provide innovative solutions to our clients. And we do this with 4 segments. So here you see an overview of these 4 segments. We have offshore energy, where we install wind farm foundations and the turbines. We have the dredging and infra segment. So we deepen harbors and fairways. We reclaim land for port infrastructure. Then we also have environmental solutions where we remediate soil for new usage. And then the last segment is DEME concessions, where we are not a contractor, but we are developing and building things such as offshore wind farms or harbors. How do we do this? We do this with our impressive fleet. We have more than 100 specialized vessels, and the 2 most impressive ones are shown here. On the left, you see an offshore installation vessel, the Orion. So foundations are installed from a floating vessel which is feeling waves and current, and we install foundations and wind turbines. And on the right, you see a mega cutter suction dredger. So we cut away soil to deepen the sea near port infrastructure, for example. So why would a marine contractor actually do CFD simulations? So it fits in DEME's strategy for sustainable performance. So we do CFD since 2020 for 2 main reasons. Over the past years, we have seen that the complexity of structures that we have to build or install is increasing a lot. And by using CFD, we are able to explore sustainable business solutions. A second reason is also to improve the performance of our vessels and tools. So we really excel in our operations. if one of our vessels can work in a higher sea state, we can do more projects over multiple years. And those two reasons, they help us in reaching our sustainable development goals. And those two reasons also reduce the need for experimental testing. So in the past, there was a strong tendency in the marine sector to build small-scale models and test them in a physical water basin. But since recent years, the computers became faster and stronger. HPC centers were there, and that allows us, apart from doing physical testing, to also run digital experiments. And I'm not saying that we fully want to replace experimental testing by computer simulations. They go more hand in hand, and I will show it later in one of the examples I will present to you. Within DEME, we cover a wide range of applications, and on this slide I will present some examples using SimCenter STAR-CCM+. First, we do internal and external flows. So the example you see here is a very long pipe system with different exit nozzles. And this piping system can be used to fill a concrete element with sand to sink on the seabed, or to spray sand under a special tunnel element. And the reason why we do these simulations is to design the nozzle diameters so we can have an equal outflow of water or sand or whatsoever coming out of each nozzle over the length of the full piping system. Another application is multi-phase simulations, where we have one of our vessels in a digital water tank, and we are able to calculate the hydrodynamic resistance of such a vessel, because the hydrodynamic resistance is directly linked to the fuel consumption. So if you can optimize the shape of your vessel, you will reduce the energy consumption, which is very important in our business. I mean, our vessels, they are not shipping vessels which transport cargo from A to B. They are really working vessels, not always the most pretty shape. So if you can improve their shape and reduce the fuel consumption, that's really a plus plus. And then a last application I can present is discrete element modeling, or the coupling between CFD and discrete element modeling. So it's a small experiment that we did to verify the settling behavior of particles underwater. So we have a column filled with water, but also full with small particles. That's the initial condition. We run the simulation to see how fast these particles are setting towards the right picture on this slide. Yeah, that's also the reason why we are choosing for STAR-CCM+, because it's a multi-physics code. So it enables us to do a wide range of applications, which is not always that convenient in other alternative codes. The hardware we are using for our CFD simulations, it's almost fully provided by the Flemish Supercomputer Center. We have seen this picture before in the presentation of Liam, if I remember correctly. So here you see the different options that the Flemish supercomputer is offering. And the main things that we are using is the web portal, so the open on-demand application, the main partition with the CPU nodes, and the interactive and debug partition. At this moment, we're not using any GPUs for solving simulations. One of the reasons is that okay, it comes with a cost, but also that we do a wide range of applications, and not all physics are yet supported on GPUs. So how do we use the Flemish supercomputer for our simulations? Well, it comes later, because it's part of our accelerating program of STAR-CCM plus simulations on HPC. Sorry. So the first step in our acceleration program is a pre-processing. most of the HPC users, they use HPC computing for solving the equations. But we are also using the Flemish supercomputer to do pre-processing. And there are actually three reasons for this. The first reason is that we often deal with very complex geometries, as you can see here on this slide. So this geometry file, it's a step file. It's much bigger than 1 gigabyte. It's about 7 to 8 gigabyte. It's very heavy because it contains every single detail in this model. So every bolt and screw is included in that geometry file. And of course, that's not directly suitable to for meshing operations. So we do interactive editing in 3D CAD within STAR-CCM+. The second reason is you cannot do everything manually in 3D CAD. So we also perform surface wrapping to make the volume or the geometry file watertight. And for that, we need high CPU speed and RAM memory, which is also offered on the Flemish supercomputer. And then the third reason is for the volume meshing. Within STAR-CCM+, we can use MPI to do parallel volume meshing. So we can run it within a single node on 128 CPUs, or even multi-node meshing is possible. So for this pre-processing, we rely on the open on-demand service provided by the supercomputer. I think Monica gave a great introduction on the open on-demand portal. I will just add a few more things. So here you see one of the interactive desktops that we're launching from the on-demand server. And how we do it is we make use of the client-server render interface that STAR-CCM+ is offering. So it's really a combination of using the right hardware with the right software. And the strength of STAR-CCM+ is that your user interface can run on a different compute instance than the server. And with the server, I mean the computer who is actually solving the equations. So to run the client, we make use of the debug node. And on that debug node, there is also a GPU available. So the client and the render are within the same debug node, and then the server is launched on a different compute node on the Rome or Milan partition. And you can see it here. If you run the NVIDIA-SMI command on the debug node, you see that the render service is really using the NVIDIA GPU. And if you log in on the compute node, then you see that STAR-CCM+ is launched on the Milan or Rome partition. And with this interactive way of working, we use the strength of the debug node for the graphic performance, and we use the strength of the compute node to do the processing, like removing details, wrapping the surface, and making the volume mesh. Now I will focus a bit more on the project that we are solving within SimCenter STAR-CCM+. And the first application is in our virtual water tank, where we simulate the motion of an offshore installation vessel. So we have a big domain of water where we put our vessel in, and we are studying the roll motion. And why the roll motion? Because it's very important for the stability of our vessels during operations. You have to imagine that this vessel remains floating. It's not a jack-up, so it's not lifted out of the water during the operations. It's still floating, so it feels the waves, and because of the waves, your vessel will start to move. And to have safe operations, it's very important to limit these motions, and roll damping is really important to limit these motions. So it's a really requirement to understand the roll damping in detail. So how did we tackle that project? If we design a new vessel, we quite often go to a physical testing facility where they build a scale model, as you can see here in the middle picture. So this is a small scale model. I think it's about 5 to 6 or 7 meters long. And the good thing about this test campaign is that it gives us data which we can use later to validate our CFD model with. So in the physical water tank, a limited range of experiments were done. So for one specific draft, which is the part of the hull under the water, for specific forward speed, and for one position of this vertical center of gravity. So that's a data set we have and that we use to calibrate the CFD model. And once we have validated and calibrated the CFD model, we can start exploring a wide range of variations in draft, forward speed, and different positions of the vertical center of gravity. And that will give us a whole database of roll damping coefficients for these different loading conditions. And that database is then used in follow-up studies to really calculate the motion of a vessel in a specific sea state. This virtual water tank is using the volume of fluid technique. So we are resolving the free surface, water below, air on top, and in between you have the interface, the water interface. And we also use the FBI motion. So the body is allowed to move in a few degrees of freedom. And we also use overset. So we make a mesh very close to the vessel. It was a polyhedral mesh, and then we have a background mesh which remains fixed and resembles our virtual water tank. All these simulations were run on a single node, so 128 CPUs, and the reason is they don't scale that well for a higher core count because the number of cells was limited. And the reason behind that is that the simulations are transient, so unsteady, and they are based, and the time step is based on the maximum CFL number. So if you make your cells smaller, you have the option to use more cores and to have more accurate solutions, but that also implies that your time step will reduce because you have a fixed CFL number that you have to satisfy. And in the end, you end up in this loop system. So using more cells will make your simulations run longer, even on more nodes, because your time step is also dropping. And that's why we have chosen for a certain number of cells with a fixed time step, and we run these simulations on a single node to make them still efficient. Another example that I want to show to you is still in our vertical water tank, where we are simulating an offshore monopile installation tool. This was for a project in France where we had to install foundations from a jack-up vessel. So it's not a vessel which remains floating during the installation. The vessel can lift it up out of the water with the 4 of these steel legs. So the vessel is not feeling the waves anymore. And what was a challenge here? In the Atlantic Ocean near France, the seabed is made from rock at some locations. And at that location, we had to install foundations. And usually in a sandy seabed, we hammer these piles in the sand, but you cannot do this in rock. The rock is just too strong. So how did we do it? We used a drilling technique. So we made a hole in the rocky seabed. We put that pile in that opening, the drilled opening. There was some small space between the borehole and the pile. We had to fill this with some kind of grout paste, which is a fluid in the beginning and it hardens over time. And during that hardening process, it was very important that that pile foundation is not moving. And that pile foundation is actually exposed to waves. So how did we prevent this? It was by using this installation tool, which is the big white cylinder here, partly above the water, but mainly under the water. And that protects the monopile from feeling the waves. So it's like a big outer shell, which is preventing the waves hitting the pile and limiting the motions of that monopile. But that protection cover, that tool feels the waves, so it will start to move. And also it's connected to the offshore installation vessel, which is feeling the wind. So there is also some oscillation from there. So in the end, that tool is oscillating. And imagine that you have like your cup of coffee and you start to move your cup, and you will see that your coffee starts to slosh. It goes up and down. And that's exactly the same what is happening during the installation procedure. So the water within this protection cylinder will also start to move, and that might induce a small force on that monopile foundation. So the question was, how big is that force on that monopile foundation, and will the motions be limited? So we placed that tool in our digital water tank. We, as an input, we know the motions of that installation tool. Again, we were using the volume fluid method to resolve the free surface outside and inside that installation tool to calculate the forces on the monopile. And also we used a mesh morpher and adaptive time step and adaptive mesh to run the simulations. So how is it looking like? Here you see the position of the free surface. The outer shell is shaking from left to right, and in the middle, so within this protection cylinder, you see the monopile foundation, which is fixed. And the output of the CFD simulation is to calculate the forces on that pile foundation to check the stability. And again, we run these simulations on a single node for the same reason, that these simulations are unsteady, and the time step depends on the mesh dimensions. So a very fine mesh requires a very small time step, and these simulations, they scale but not perfectly. So that's again a motivation to use a single node for a specific cell count. And the good thing about the Flemish supercomputer is that they not only have a lot of CPUs, but also the quality of a single CPU is very good. So if you stay within a single node, you can use the latest generation of CPUs to have your results within a feasible time window, which is something like a few hours, maximum 2 days. Then the last application I want to present to you is another offshore installation vessel, but this time in our virtual wind tunnel. And with this simulation, we want to understand the forces on the installation vessel. Because during an offshore operation, we have to make sure that the vessel remains in position. And how is it done? On that vessel, there are 6 or 8 thrusters which maintain the position of the vessel during the operation. And to design that, it's called dynamic positioning. To design that dynamic positioning algorithm, the wind force is an input value. And if you know that wind force very accurately, you can design your DP system quite good, and you are allowed to work in higher sea state or higher wind conditions, because you can estimate the wind forces much more accurately, and you need to introduce less conservatism in the design. So within this digital wind tunnel, we are free to put any geometry we want. So we can have variations in deck layout. We can easily change the wind speed and the wind direction. For this simulation, we have chosen to use the text eddy simulation, which is a combination of Reynolds average Navier-Stokes simulations and LES simulations. So RANS is used in the far field, where we are not interested in the turbulent fluctuations. And LES is used in the regions where we have enough mesh resolution, where the time step is small enough, and then we can really simulate the turbulent fluctuations over time. And the output of such a simulation is the forces and moments on the vessel. But we can also see some interesting flow features, like we see that the crane is creating quite some turbulence. And with this simulation, we can also check or verify safe helicopter landings on the helicopter platform, because we are far offshore. Crew needs to be changed, and one way that can be used is to use a helicopter, and we want to have safe operations for our crew, so we have to limit the turbulence on top of the helideck, or to verify that turbulence is limited above a helideck. And one way is to perform these very intense DES simulations, which is a combination of RANs and high fidelity LES in the regions where we have interest. And this simulation actually scales very well on the Flemish supercomputer. So we were not restricted to a single node. I did some checks the past weeks to see how good it scales. So the simulation in the numerical wind tunnel was consisting about 26 million cells, and I was using the Milan partition. You see 3 lines. The dark line is only using 50% of the available CPUs within one node. So I was requesting the full node, but I was only using 50% of the CPUs. The green line was using 75%, and the blue line was using all the available nodes, all the available cores within a single node. And what you actually see is if you use a single node, so the most left dots on top of this graph, you see that the averaged elapsed time per iteration is more or less the same if you would use 50% of the node or 100% of the node. So this shows that, okay, it's better to use the full node because it's it goes a little bit faster than only using 50% of that node. What else do we see is that the more CPUs you use, the faster your simulation run. Up to 2048 CPUs, which is, I think it was 16 nodes that we were using. And then we saw a deviation from the 100% efficiency line. So by using the Flemish supercomputer, we reduced the simulation time of a single simulation, which would take weeks on a desktop, towards 3 or 4 hours on 16 nodes. So that enables us to do different wind directions, different wind speeds, and different deck layouts of the one specific vessel. This is another graph showing the scalability of STAR-CCM Plus on the Flemish supercomputer. The dashed line is now the 100% efficiency line, and we see that for if you use the full node, so the light blue line, we have even super linear scaling. So if you double the number of CPUs, your simulation time is lower than 50% of the original case. And I think the reason behind that is, I double checked this with a support engineer from Siemens, is that the L3 cache within the AMD Milan CPUs is quite high. And if you use more CPUs, you're almost putting your whole problem into the L3 cache of your CPU, which is the fastest memory you have available within that CPU. So to conclude this presentation, some takeaway messages, how we enhance our sustainable marine solutions and operations by STAR-CCM Plus CFD simulations on the Flemish supercomputer. So we really need the HPC to make our simulations feasible, to have results in a short time window, not only for solving, but also the pre and post processing, which we do on the Flemish supercomputer by using the debug node and the available GPU on the debug node. It's also important to keep your data close to the computing power, that you're not losing any time by transferring simulation files from external HPC providers towards your corporate network. A third point is that not all applications, they scale in a similar way. Like if we have unsteady flows, which require a maximum CFL number, the scaling is not as good as like a digital wind tunnel with RANs of DES or DES, where you can scale up to 2000 CPU cores. And last thing, very important, is that CFD simulations, they still require laboratory or field data for validation and calibration. So what I believe is that CFD simulations will never replace field tests, but they will make us smarter how to prepare these field tests. It's really the combination of digital techniques with physical techniques. And your digital techniques, you can accelerate them by using HPC, for example, the HPC provided by the Flemish supercomputer. And that's it. Thank you.